Hello and welcome to 26th lecture of the course on corrosion, environmental degradation and surface engineering. The present lecture we will be discussing about the failure mode and effect analysis. Lecture 25th also was on failure mode and effect analysis. So, this is in a sequence, maybe second lecture on FMEA. What we discussed in previous lecture is something like how to apply FMEA on existing product which is well established like a journal bearing. Now, in this lecture we will be taking a new product, we will be naming this as a passive magnetic bearing, and then some sort of the failure modes of the passive magnetic bearing and how they affect the operation. This topic is relatively new, reason being passive magnetic bearing have been utilized, but we do not have extensive literature available, particularly the failure mode. Most of the literature which is available on the mathematical modeling of the passive magnetic bearing and then some success stories. But we know very well, unless we know the failure modes, we will not be able to overcome the major problems. So, that is why we made magnetic bearings and we try to diagnose whether magnetic bearing are really working well or not, and whatever the possible failure which were initiated maybe because of the lack of the knowledge, lack of the fabrication facilities or maybe assembly, manufacturing, those problems emerged and then we try to point out. This complete the lecture has been picked up from a literature which is our publication, it was published in 2016, and then the title of the paper itself is a failure mode and effect analysis of the magnetic bearing. It was published in engineering failure analysis. So, I am going to cover it and keeping in mind that we need to really focus on the lecture, not only on the research, and try to cover this as a case study, try to elaborate in a manner. So, it is a simplified easy way to understand. Do not go in a very sophisticated mathematical models, do not go in a finite element models or go in a kind of the finite element which are really required for magnetic calculation. So, in this case what we have done some experiments to figure out the severity of the failure modes and in addition how to detect those failure modes. So, these are the two important aspects, to first figure out what are the failure modes, then how to detect that. And then based on those calculation we figure out what is the RPN number, which is a major number or a major factor to understand the failure mode and effect analysis. Then suggest some corrections when, as I mentioned, that FMEA itself is an iterative procedure. We figure out what are the problems and we address problems which have a very high RPN number. After that we do modification, again after doing modification we need to make again a worksheet related to the failure mode analysis and then do corrections and then again experiment it to figure out whatever we have done is correct or not. So, that has been done, correction has been implemented and further experiments were carried out to demonstrate the proposed remedial whatever the remedial solution were given are really functioning properly. Now, let us start the lecture. What we say that FMEA first step itself is to understand the product, to review the product, study the product, and the product is not existing, do some sort of experiments on that. First is a mathematical model, do a mathematical model, then fabricate the unit, then perform experiment and then start FMEA also on that. So, in this case if you look at that the figure has been shown in passive magnetic bearing, it appears more like a journal bearing. So, I am able to connect this with a journal bearing which has a one shaft, one in this case housing or maybe the bearing. So, in this case shaft or in the journal bearing we use the word journal or in the magnetic bearing sometimes we use a rotor. These are more or the same, and in this rotor shaft or journal in a PMB is maintained in the air itself, right. So, we have a separation from sleeve or bearing and then shaft remains in air, suspended in air, and because of that we will be getting almost negligible friction, and friction is happening, it will be happening because of the air cutting, air resistance. There should not be any contact between the two surfaces, reason being we are assuming that there will be strong repulsion force between the magnetic surfaces. What are those magnetic surfaces? We will be mounting one ring or maybe say on the shaft itself. So, that portion which is in a bearing, which can be called as a journal or rotor, and in a housing itself we will have a magnetic a permanent magnet. So, permanent magnet versus permanent magnet, and we are trying to keep a repulsion force. Repulsion force will have a separation between those two surfaces. If the two surfaces are separated, then there will not be any mechanical contact, and if there is no mechanical contact, there will not be any wear at all. And in this case, we are keeping a separation and then the fluid or separation media as a air, then I do not really require extra liquid lubricant or solid lubricant from outside. So, that is the advantage, no need of the lubrication, zero wear, almost negligible friction, because air density or air viscosity is very low, and the resistance will against the shaft rotation will be very low unless the RPM is very high, like a 1 lakh RPM or something like that. So, question of the friction will be not there, or maybe say almost negligible friction. Another one thing is that now in recent time, neodymium iron boron magnet has been available, easily available, and that to a reasonable cost, reasonable price. We can buy a number of magnets with the cost of the 10,000 rupees, which is pretty cheap in this case. And then these are easily available, you order it and you will be getting those kind of magnets. So, we can say that it has a good number of advantages: zero friction or maybe negligible friction, zero wear, no need of lubrication, availability of high strength neodymium iron boron magnets, and that to the low cost. Now, because of the so many application, now these kind of bearings have been utilized in the flywheel, in some like artificial heart, maybe the molecular pumps. So, there are number of application of the PMBs or maybe the permanent magnetic bearings. So, there are many applications. Question comes how they apply and then how they really control it. Most of the documents which are available, they do not give complete information. There is some information, but it will not be complete, and the technology, if you are trying to buy from market, either you buy as it is a product, but if you buy a technology, it costs a lot. So, naturally we need to develop a technology whenever we are thinking about the magnetic bearing. Now, what are the problems which can immediately come in a mind is something like when we are talking about the neodymium iron boron magnet, and if the size is increasing, so large size of the neodymium does not have a regular magnetic field. So, if I assume there is a permanent magnet, maybe in a suppose a semi sector or maybe say a half sector, in this case 180 degree, the question quite possible magnetic field will not be the uniform across the whole surface. So, there will be some sort of non-uniformity, and we need to model those things. So, in this case, because of unevenness of the magnetic field, there is a problem. In addition, this field will further become uneven with a time. So, there is some sort of a demagnetization of the permanent magnet. This is like a common process, and then maybe demagnetization happens after 1 year, 2 years, 3 years, and there are number of modes of the demagnetization itself. Another thing is that if the little bit variation we can model appropriately, maybe we can take some factors and then we can implement design in such a manner that up to 5% change in magnetic flux density over the surface will not really give it the more problem. But if it is exceeding 10% variation, actually there will be some sort of unwanted vibration in the system, and then because of unwanted vibration in the system, it will create an unbalance or imbalance. Now, if there is unbalance or imbalance, shall we use active magnetic bearing, which is basically used for the controlling shaft position to the accurate level. So, permanent magnetic bearing, once you design, you cannot change, while in active magnetic bearing we can change it. So, we have one publication also on active magnetic bearing, particularly fault diagnosis system. No, I am not going to describe that about electronic system, but I am just mentioning whenever there is a more sophistication is required, we add active magnetic bearing with a permanent magnetic bearing, so that we get overall good solution. but in this case I am just focusing only on permanent magnetic bearing, and then we say that because of the variation in magnetic field there will be possibility of an unsteady motion of the rotor. It will cause a vibration problem, and then that's how, and then if really goes and strike against the stator, and permanent magnet being very fragile, it can break the permanent magnets also. Once the permanent magnets are broken, then complete failure occurs. So, these are the major issues. We have a good number of advantages, but there are some risk, severe risks. That is why the RPN value is important to calculate and then do a remedial action on that. Let us see, as I say that this paper is already published in 2016. I am considering this as one of the case study. Now, here there are 3 figures have been shown, figure 1, figure 2 and figure 3, and in the 3 we have used a different kind of configuration. If you look at in the case of the rotor, or maybe the shaft, or maybe the journal on which is mounted on the shaft itself, we are using some sort of the permanent magnet. In this case there are 6 magnets, in this case there are 4 magnets, in this case there are 3 magnets. We are using this kind of the magnets on shaft, while in case of the figure 1 the stator we use a 360-degree arc, that means a full circular or cylindrical magnet, while in the case of configuration 2 we use a 180-degree, and last one we use only 90-degree, right. So, there is a variation. We want to see what is will be the shape factor effect, or maybe say full circle, cylindrical, half cylinder, or maybe the 1/4 circle cylinder, what will be the impact of this shape on the permanent magnetic bearing behavior. So, this is what we have done. Passive magnets can be arranged in a variety of ways to form the permanent magnetic bearing. We tried 3 layouts which have been shown in figure 1 to 3. And then what is the configuration 1? This is what I am showing. Figure 1 is a configuration 1, figure 2 is a configuration 2, and figure 3 is a configuration 3. Now, what is the figure 1 configuration? We use a 50 mm the full ring stator magnet, the full ring, the 360-degree, that is what I have been mentioning here. Of course, it is and then the rotor is also been utilized as a full ring, and then this is a 48 mm OD, and then we use 8 mm thickness magnet, the 6 magnet, to make it the 48 mm length as such. Now, coming to the configuration 2, we use the half ring, a 180-degree the stator magnet, and then we use the 4 magnets in this case. So, the 8 plus 8 plus 8 plus 8 makes 32. So, in this case length is 32, but we kept stator length as a 30 mm. Coming to the third one, we use only the 90-degree sector at the bottom, and now to bring more stability we use a 45-degree arc on the top also. While in this case we kept stator length as a 24 mm, and this is a 8 mm, 8 mm and 8 mm. So, this 8 plus 8 plus 8 is a 24 mm. So, this is the rotor length is a 24 mm, that has been mentioned here. And then so this is what has been done as such, 3 segments. Now, what are the merits and demerits of the 3 configuration? We say configuration 1 has a high rigidity, stiffness will be very high in this situation, but load carrying capacity will be very low. So, we can do a detailed mathematical model, but for time being I am not going in those modeling cases, and I say that this has a higher stiffness but low load carrying capacity. And then configuration 2 has the high load carrying capacity, because if you know the 180-degree arc and then weight is downward direction, immediately repulsion will occur, while if it is a 360-degree, repulsion will come also from a top also. The load carrying capacity will come down, while in this case load carrying capacity will be enhanced, increased, but there will not be any stiffness from the top. So, top stiffness will be removed, maybe say almost 0, and it will hit on the outer surface. That is why we wanted to know what are the different configurations, and then how do we study stiffness and the load carrying capacity based on these configurations. So, configuration 2 has a high load carrying capacity, but low load stiffness or lower stiffness. Configuration 3 has a moderate stiffness and moderate load carrying capacity compared to the configuration 1. In this is the way we have done, very high load carrying capacity, but almost negligible stiffness, moderate load carrying capacity and relatively moderate stiffness, and then what we say the low load carrying capacity and the high stiffness. So, these are the 3 configuration we kept. In addition, we made one experimental setup to perform experiments, and you can see here the disc has been mounted. Now, I can create any kind of unbalance because there are number of holes in this disc. If the disc has a number of holes, I can put any number of bolts in that, even maybe you must have done this kind of experiment in the lab when we want to create some unbalance, some eccentric loading in the rotor system. This kind of setup can be utilized here, and then here you can see here that aluminum housing or stainless housing can be utilized, and that this we have made on a T channels. So, in a T channel basically housing will be mounted rigidly. If I use a drill a hole and then mount it, then maybe the rigidity of the housing will be lesser. So, in this case we try to fix housing and then rigidly on the base plate, and then there is a split housing. You can see the top half of the housing has been connected whenever there is a need. Now, we also did an experiment on the hybrid mode, but presently in this case study we are considering only permanent magnet. In a hybrid mode we have not yet started working on the liquid lubricant. So, in this case we also worked on the liquid lubricant to help to reduce the vibration, to increase the performance. Those things maybe those are separate papers, but in this case I am not going to discuss about those. So, what is this experimental setup? In this case the experimental setup was designed and built to handle the 3 magnetic bearing configuration which I mentioned. Stator magnet were attached to the aluminum housing. In this case we have used aluminum, it can be stainless steel also. Aluminum is a better option. It can be securely, it should be securely fixed on the T channels that has been done, which is on the base plate. And the rotor magnets were mounted in a stainless steel. If I use a ferromagnetic material, what will happen? Dissipation of the magnetic field will occur. So, we want to retain the permanent magnet strength only on a short span, maybe only in the rotor side, or maybe the rotor which is mounted on a shaft, which is a stainless steel shaft, and this has been used as stainless steel shaft, what is being shown here. Now, how the overall configuration means, one end of the shaft is free, another one is coupled with a induction motor, and then you are able to see there is a motor here, and there is a coupling which will be maybe in another diagram. I will show more clearly that there is a spiral coupling on that. We use a ABB frequency drive to change the rotational speed, to figure out what will be the impact of the rotational speed, and visually what problem comes when we are running this permanent magnetic bearing on some steady speed, then we do not find many problems. But coasting up and coasting down, that means increasing speed to the certain level and then finally shutting down to decreasing, that time we find a lot of instability in a magnetic bearing, and that is what we wanted to study. What will be the performance under the transient condition? And we find that permanent magnet bearing will not be very good option in a transient condition, and it may require some sort of additional support, either hydrodynamic action or maybe active magnetic bearing action. Those things are really required. Now, in this table we have given all the details. You can see the rotor magnet axle length has been shown in configuration 1 48, configuration 2 32, configuration 3 and the 24. Then OD has been kept in all 3 cases 48 mm, because the rotors are the same dimension, and ID in this case it has been mounted on the shaft. So, my ID of the shaft has been maintained as a 5 mm. So, that most of the rotor the magnet have been mounted on a 5 mm shaft. Coming to the stator magnet, we change the length. In one case the slightly the bigger or maybe the longer compared to the rotor magnet, other case slightly shorter, and third case slightly bigger. Now, this can be we can do this permutation combination and come up with the right figures, the right equation, or like we can use the PCA on this. but for present case only we are just concentrating only on FMEA, and we do not want to go ahead with any other topic. Now, this has been shown, and then in this case rotor weight has been mentioned clearly. Rotor weight has been kept various thing because it depends on the magnet length. Then in this case maximum length of the rotor, then the 600 grams, while 32 in this case is around 400 grams. In the 24 length it is a lesser, something like that. So, this is the loads which have been shown, and now in different configuration we applied the load also different manner. Now, why we have kept a maximum load in the configuration 2? Because load carrying capacity in this case is very high. I can't go ahead with a low load carrying capacity. In the low load carrying capacity, low applied load, what will happen, rotor will go and hit the out bearing or maybe the housing surface, and that will be more problematic. So, passive magnetic bearing can be designed as per the load situation, what is the load or maybe RPM situation, whatever the load operating condition is being given either in the applied load, maximum load carrying capacity, or in the rotational speed, or maybe that on the tangential speed, whichever is been available to us. Now, what is the step? This was step 1 to study the product. So, that is why I have given slight introduction of the permanent magnet and how the magnet have been manufactured and then assembled and what are the dimensions. So, this is just sufficient to know our system as such. Now, second thing is that identify components which are prone to failure, which component will fail. So, first thing is a rotor magnet which is been mounted on a stainless steel shaft will make possibility it has a possibility of the failure. Then second thing is that stator magnet which also may fail. Then comes casing in which the stator magnet has been used or maybe the fixed, that casing may fail. And then this whole the magnetic bearing assembly is connected with the motor with the coupling. So, there is a possibility of coupling failure. So, we identified rotor magnet failure, stator magnet failures and casing and couplings. So, these are the possible things. Now, let us start with the rotor failures. What there may be a number other failures, but we in our case we found 5 types of the failures. We say 5 types of the rotor failures, and then particularly we perform experiments and then we found the failures. Now, those failures are what, which category? As I in previous lecture I mentioned that we need to categorize. Now, in this case wear is a one category, cracking is another category, and demagnetization is a third category. The new thing which I have understood is a new pole development, and this is new pole development, whole technology of new pole development is being utilized in magnetic particles. That is what we have studied in the non-destructive testing on magnetic particles. Whenever there is some sort of crack or subsurface crack, what will happen? A number of poles will get formed, and because of that, and wherever there is a crack inside a surface or over the surface, suddenly magnetic field will increase significantly, and that is what we are going to describe in this lecture. And because of the change in a magnetic field, instead of one north and one south pole, there will be many south poles, many north poles, and that is what really is worrisome, particularly in a permanent magnetic bearing. And last one is a fracture. So, 5 categories, one is a wear category, cracking category, demagnetization, new pole development and fracture. Now, when we start thinking about the rotor wear, we use permanent magnet bearing assuming there will not be any wear, but here we find first thing is a rotor wear. And actually something has gone wrong, either we do not have sufficient knowledge, or maybe there is a manufacturing error, or maybe there is assembly error, something. So, that is what we are trying to dig out. We say rotor magnets, and in this case basically stripping of the coating happens. So, whenever we purchase the permanent magnet, on the top surface there is some coating, and when you operate and in operating condition, we find there is a scrapping of the coating itself. You can see before use the permanent magnet is shining, and after use because of the wear, we are able to see major patches of the wear or maybe a worn out surface here. Same thing happens at configuration 2 also, you can see here the wear of the surface. So, even the permanent magnet, if they are not well designed, then it will cause a rotor wear as this is. Now, another one we also found that is a number 2, that is a crack. Now, in this case permanent magnet and here the surface has been shown as a cracked one, there is a crack here, and then configuration 1 and then configuration 3 also we found the cracks. And as we know very well, the permanent magnets are very brittle in the materials, and even the impacting, little bit impact on the surface may cause some sort of cracking, or maybe say even the splitting of the magnet into half or maybe more than 2 halves. So, these things have been mentioned and clearly indicated. Now, coming to the wear side, what we found the rotor wear corresponding to their configuration has been shown in figure, and major thing in this case we also found the increase in the temperature. We otherwise in permanent magnet bearing there should not be any temperature rise, but here because there is a mechanical contact between two surfaces and there is a rubbing and scraping of the coating, that there is a more friction. So, higher friction and higher temperature. So, permanent magnet bearing which was thought it will give a very good solution, low zero wear, negligible friction and almost zero temperature rise, all bad thing happened to this system. Now, coming to the crack, as I say that this what we have realized that this happens because of unsteady rotor motion. That means, whatever we want the shaft should rotate at the concentrically at the bearing center, it was not happening. It is something like a random motion of the shaft and what we say unsteady rotor motion. And another thing because the unsteady one and there was not sufficient stiffness. So, there was a infrequent collision or maybe the sometime collision between with a stator also happened, and because of this collision between the two permanent magnet, the cracks starts. This has been mentioned. As a result, rotor magnets get cracked or this particular phenomena was observed during the coasting up and coasting down periods. That means, when you are starting the motor and motor start from rotating from 0 to 1500 RPM, there is a possibility the rotor will go and knock 2-3 times stator. Same thing when you are after running for 1500 RPM for some time, maybe 3 hours, 5 hours, whatever, you want to shut down that, come to the 0 and then it will go again hit. There is a problem. So, now in this situation says that and whenever the coasting up and coasting down period comes, we should use some other support system. There is a one possibility. So, that is what we learned from doing this kind of experiments. The next one was a demagnetization, and we also learned that if we are using permanent magnet bearing and then there is a rotor magnet, there is a stator magnet, and if this there is a difference in the magnetic strength of a stator and a rotor, what will happen due to difference in the magnetic strength between rotor and stator, what will happen, the stronger magnet will demagnetize the weaker magnet. Now, in this case we use a stator magnet which has a magnetic strength of 1.4 Tesla, and we use a rotor magnet which has 1.04 Tesla. So, this was what we purchased a magnet and then that had a magnetic strength, and then because of this demagnetization of the rotor happened. So, in this case demagnetization of the stator did not happen, but the demagnetization of the rotor magnet happened, and now because of the change in or maybe difference in the magnetic strength. That means, we have learned that magnetic strength of the material should be same, and that is why finally when we started working, we find that we are not getting this kind of stator and the rotor which have a same magnetic strength. That is why we made some different configuration. We will discuss those after 4-5 slides. Now, we say the demagnetization of rotor happened if it is a magnetic strength is a lesser than the stator magnet. However, if we keep a same magnetic strength for the both, at least this kind of demagnetization will not occur. However, there is a possibility that if there is a mechanical contact between the two permanent magnet, again it will cause some demagnetization. If there is a hitting or mechanical action is happening and there is some sort of knocking is happening, then again the demagnetization is possible, and that has been shown over here. We can say that in this case figure 3a, we are able to see there is an offset. That means shaft the shaft has a rotors and rotor is in the permanent magnet stator, there will be some sort of a shifting it will not be self-centering of the permanent magnet bearing. However, we know the permanent magnetic bearings are well known for self-centering purpose, while even in the configuration 1 we do not find that self-centering is happening, and there is some sort of a demagnetization, and this is what has been shown. Now, if you look at in the unused rotor magnetic strength, we find the magnetic strength, or these are the data related to magnetic strength. Now, coming to the used rotor, you can find that magnetic strength is a one side, is a similar one, but here the demagnetization has happened, here the demagnetization has happened, here the demagnetization has happened, here the demagnetization has happened. That means there is a possibility that this kind of surface has hit the housing one way or another way, or housing, or maybe the stator, whichever is available. So, there is a change in a magnetic field. That is what we mentioned. The figure 3.3b depicts a variation in magnetic field along the circumference before and after experiment. So, before experiment we do not find variation across the surface that much. There is a difference, the stator magnet had a high magnetic field, then the magnetic strength 1.4 Tesla, while the stator had the rotor had a 1.04 Tesla, but in this case even the 1.04 Tesla was further reduced. Now, imbalance caused by the rotor magnets, this is because of the non-uniformity of the permanent magnet, it will cause an imbalance, that means eccentric motion of the shaft, and that will be creating some sort of disturbing forces in a permanent magnetic bearing. So, this is another problem related to the permanent magnetic bearing. Coming to the fourth one is a pole formation. What we find, there is a, suppose you have a pole finder sheet available in the market. Now, if there is a uniform magnetic field and there is a maybe single north pole and single south pole, then there is no issue. You will find more or less all the black color over here. But if you, and of course there is a if you find there is a this line fluorescent color line, that means there is a change in a magnetic field. So, if we are attaching permanent magnet axially, it will happen, but you can find here there is a more generation, or more possibility of the north pole and south pole generation. That means either there is some rubbing happen and then surface has been rubbed, and that is why the more and more poles have been generated, or there is some sort of cracks, and as I mentioned, this whole magnetic particle non-destructive testing is based on this technique. They try to figure out that if there is something more the south poles and north poles, all the magnetic particle will go and stick to the surface, because there is a huge variation, number of poles will be there, and then wherever there is a pole formation occurs, suddenly the intensity of the magnetic field will increase. And this is what we say the pole formulation, continual rubbing of the rotor against the stator forms a new poles in the rotor. So, it is not a single pole, maybe say there may be a number of poles which will be showing in the subsequent slides, that how it happened and how we figure out. And we use a pole finder sheet which is available in the market to determine the formation of the new poles, and this is the figure shows the use of the pole finder sheet on the rotor. That is what we use, and then we figure out. Coming to the final, which is a drastic one, there is a fracture. Maybe there is a one crack in this direction, there is another crack in this direction, they merge and whole half the 1/4 maybe say the 120-degree magnet is been ruptured or coming into 2-3 pieces, it will come out. So, this is a drastic failure also. So, permanent magnetic bearing which was supposed to work very well nicely and then give a negligible friction, zero wear, and win-win situation for the as a bearing solution, but it failed badly. So, this is a rotor magnet fracture, the result of the strong collision between the stator magnet and rotor magnet and the stator magnet, resulting in a catastrophic failures. So, in this case particularly FMEA EVTU was is really appropriate to utilize and come up with how we go ahead with the solutions. Now, this was a rotor related. Now, next one is the stator, second component, and we also found a similar kind of because that there is also permanent magnet and relative speed and some sort of a loading. More or less the failures also are more common in this is the wear category, cracking category, demagnetization category, new pole formation category and fracture categories, kept in the same way whatever the 5 categories we studied for the rotor. Now, in one slide I am trying to show all those. You can see here the some sort of a cracks in the stator one. There is some sort of a crack in axial direction. This configuration 3, you can see the number of cracks. Now, these are the configurations that have been shown. Now, interestingly when the demagnetization happens even after cracks also. So, there is a crack formation, demagnetization will happen, and interestingly you can see here there is a crack which is passing like this. Now, here the magnetic field is around 760 Gauss and maybe here 660, then 550 and minimum goes to 250. Right. So, there is a huge variation in the magnetic field, it will create a lot of disturbance and then rotor will really vibrate a lot. So, that is what has been shown over here. Now, this is the demagnetization. Coming to the new pole formation, you can see if the new magnet there is no green color visible as such, that means permanent magnet which has been there does not have many poles in this area. Now, but if you install this permanent and then the pole sheet in particularly the damaged magnet, you can see there are so many green color lines. So, the green color is visible in this case, there are many green color lines in this case, that means there are some poles. Not only this, you can look at in this case also we are able to find many green colors in this also. Even in this case also in the figure 1 maybe the configuration 1 we are also able to find out green color. So, there is a number of rubbing marks, crack marks and we are able to see those things, and finally comes a fracture. If there is a deep crack in this case, if you try to remove whole piece it comes out, and then this also we found the top view in this manner. So, there is a that has been shown in the side view or maybe the front view in this case, and this is the top view, and then we can remove this complete piece, that means the magnet has been fractured in the 2 pieces. So, this is related to stator. Now, coming to the third part, that is housing. Even in housing we found particularly for configuration 2, because we use only 180-degree arc at the bottom, top was without any arc, and we find that rotor has the rubbed against housing also. So, that is what the contact region has been shown, and the last one is a spiral coupling. You can see that the spiral coupling also has failed. That means there is some sort of unbalance in the rotor, and then there is a more compression, extension, compression, tension, and because of that there is a fracture of this spiral coupling. So, that is the bad failure as such. So, what we say housing failure modes, rubbing of the stator at the top of the casing occurs in a permanent magnetic bearing, reason being only half of sector magnet which was kept purposefully to increase the load carrying capacity, but it has failed, reason being there was no stiffness to resist the motion of the rotor. However, because of the top side PMB has no rigidity, rotor scraps against the top housing during the rotation, resulting in case wear or maybe the wear of the casing, and that has been shown for the configuration 2. The failure of the coupling, we say spiral coupling, connect the shaft holding the PMB's rotor to the motor. When the rotor rubs against the stator, frictional force increase significantly, and because of that there is a more torque, and then the motor has to provide those torques, and then in this situation particularly spiral coupling fails. This increase in the torsional coupling torsional load and the spiral coupling causing it to fail, and the fracture, I mean the whole spiral coupling also fractured in 2 pieces, and then that is here it has been shown what I have underlined here. You can see that there is a coupling comes out in 2 pieces. Now, step 4 is basically getting what is the severity rank, what is the occurrence rank, and then what is the detection rank. Now, in previous case study we consider 1 to 10 ranking, while this is a relatively new component. So, we thought maybe new system, we thought that better we give rank between 1 to 5. whenever we have a relatively new system, we do not have sufficient knowledge, we will give a rank from 1 to 5. If we have a little more knowledge, we go with a 1 to 10. If we have extensive knowledge, we will go ranking from 1 to 100. So, in this case 1 is the lowest score and being 5 is the highest. Keep in mind lowest NP is really required for us. So, that the lowest number will be useful to us. Now, coming to this one, this ranking can be given based on the existing knowledge. If you have expert opinions, or maybe in this case we did a existing knowledge, we try to do a number of modelings and then we did some experiments and then we figure out the values also. And the expert opinion, we could not figure out nearby who is the expert in this area. So, we could not get a expert opinion in this case, but existing knowledge which is available in literature, we use it and then we did a testing on that. Now, coming to the first case, so the severity, how do I find the severity? In this case, as I mentioned, that we do a theoretical modeling and then we do experimental studies to figure out severity of the failure and rank according to that. For that purpose, what we did, we have some softwares available. Those softwares were also utilized to get more and more knowledge. So, formation of the surface crack on a magnet, we figure out using the pole sheet that there are many north poles and many south poles. So, formation of the surface crack on a magnet, we figure out that it will alter the characteristics of the magnetic field and then it causes the failure of the permanent magnet. We say that this is a progressive failure condition leading to the catastrophic failure or catastrophic fracture, and then we use a finite element method. I am not going in those details, but I will just show the results of the magnet with a crack. Now, what has been done? Now, we can see here the virgin magnet, a new magnet, no crack at all, and then if we make a crack through and through across the length and then maybe give a 3/4 version, no crack, 1/4 thickness crack, 1/2 crack, or maybe say 3/4 crack, some sort of study can be done. So, magnet with a crack, but having a different dimension, those things were simulated. So, what we did in this case, as I mentioned, the virgin magnet, we took a 180-degree arc sector magnet, ID was given as per the requirement, OD was given, thickness was given, and maybe thickness in this case is a length was utilized. Here we are showing solid representation and then we use the ProEngineer software to model it, and in the beginning of the FMEA I mentioned that we require the drawings or we require 3-dimensional model to utilize the FMEA in a better manner. So, in this we did that and we say on this magnet various type of the cracks which has been shown here were depicted. They mentioned very clearly the ProE software was used to make a 3-dimensional model, and then we use the software, the Maxwell and Soft 14 software, which is especially used for the magnetic field analysis, that was utilized to analyze and then come up with the results. So, there are some results here. As I mentioned, Maxwell and Soft, what was the major feature which we utilized in this case? That was adaptive matching feature. What is the meaning of adaptive matching feature? I initially can select some sort of element, a tetrahedral element, or maybe initial number maybe 10,000, 15,000 something, and then we can start with that. And the good thing about this adaptive matching is that in this case particularly we initiated number of elements around 42,000, and because of the each pass after the pass 1 software itself decides the number of elements should be increased, the number of elements should be increased. Finally, it comes with some sort of convergence criteria, and convergence criteria in this case particularly was related to energy, that the continuous calculation of energy and energy error should be minimum as per the requirement of the software of what was mentioned in the software. So, those things were given here, and now you can see here number of element started from 42,000 and went up to the 1,58,000, maybe almost 4 times increase in the number of elements and to analyze a permanent magnet crack and the different cracks in this case. So, what we consider the 5 cases of the crack, One is the magnet without any crack at all, no crack at all. One is 1/4 of the magnet thickness, as I mentioned that this is a thickness. So, 1/4 of the magnet thickness, then 1/2 of the thickness, then 3/4 and then through the crack. Will there be significant variation if there is a crack happening in this manner? Now, I have shown results also. You can see maybe I can represent the results in this manner. If there is a south pole on the surface one end and the other end surface is a north pole. So, there is a continuous flow of the north south pole and there is a definite structure. While if there is a crack, what will happen? There is a south pole, there is a south pole and new north pole will start coming, and this is a major problem. There was a repulsion, there was supposed to be the surface should be repel the surface, and suddenly the pole changes. So, repulsion will become attraction, and because of this attraction the wear is bound to happen. The surface which are supposed to repel not attract at all, and because of the new crack formation and there is a change in a magnetic field changing from a south pole to the north pole, and we find that there is a major issue. So, if there is any crack in a permanent magnet, results will be very bad, and that is why we need to avoid those kind of cracks. So, what we say that for every type of the crack, one thing is that sign of the magnetic field changes near inner surface of magnet, that is what we indicated here. This is the inner surface, and then as there is a crack starts, even in the surface itself the field will change, and increment of the magnetic field was observed. So, if the edges there will be lesser field, but wherever the crack initiation suddenly magnetic field will increase significantly. That was a major the finding from this analysis, and say the sudden change, a sudden increase in a magnetic field in vicinity of the crack will be observed. Now, this has been shown in graphical manner over here, and in last time I mentioned wherever the graph we can do digitization, we can do a good analysis based on that. So, in this case we can see here without crack we do not find any variation in a magnetic field. This is the violet color line has been shown, no crack, no change in the magnetic field. While in the 25% crack, the blue color line, you can see there is a drop. Sudden magnetic field changes from positive to the negative side. Then coming the 50%, 75%, 100%, in every case there is a change in the magnetic field. That means initiation of crack itself is sufficient to change the magnetic field, and then there will be continuous progress of this crack, and knocking will happen again and again in this case. So, what we realize that even if starting from 1/4 of the length to the full through crack, load carrying capacity and the magnetic field variation will be almost 17%. We do not really worry too much about this 17% or maybe the field variation is 17%, but main thing is that whenever there is a start of the crack itself is going to lead. So, that means initially crack formation itself is a major issue for the permanent magnetic bearing. Now, we say that to evaluate the performance of PMB of permanent magnetic bearing, then what we did a sensor analysis to figure out what is really happening, and detail of this will be given in the next lecture when we will be discussing about the maintenance aspects. So, this is somewhat related to the maintenance. So, what we use are two proximity sensors to figure out what is the rotor position with respect to the housing position. Is really rotor being concentrically placed at the proper way, or it is really going and hitting again and again stator. That is why we use two proximity sensors, and these two proximity sensors they generally give the motion of the rotor or shaft in x direction and y direction. We use a DAQ system which was purchased from National Instruments, and then we use a LabVIEW interface to plot the results. And then again in this case only initially we consider the 7 different cases for the configuration 1, PMB without any defect, PMB with a wear mark, PMB with a stutter with a wear mark, rotor with a crack, stutter with a crack, demagnetization of rotor, demagnetization of stator. So, these were the 7 situations which were considered for the experimental work, mounting two proximity sensor, capturing a data, that is what data driven approach which I mentioned in my previous lecture, and this is going to give us some sort of a lead to the maintenance aspect. So, what we got it? You can see here very good PMB without any defect. We find very good behavior of the rotor. It is a concentrically placed like this dot, no change. It runs smoothly for the hours and hours and hours, no problem. Now, even the mechanical wear, maybe what we say that mechanical wear happens somewhat. Again we find maybe this dot has changed to the little more dimension, but is again that is major issue. Same thing with the rotor wear or stator wear. So, rotor wear and stator wear are not really causing major issue in this case. However, rotor wear and stator wear will change the magnetic field because we have found number of north poles and south poles also. So, that is going to be really affecting it. However, we did not find in the proximity sensors this kind of behavior. Coming to the cracked rotor, you can see the chaos. The really rotor goes hits again and again housing, even though there is gap of the 1 mm, like overall diameter clearance was a 2 mm, it hits again and again and again and damages the whole surface in a very short span of time. Coming to the cracked stator, it is not that kind of sensitive. Cracked rotor is a major issue, cracked stator is not that much issue. So, these data, of course, in this case you can see this is slightly bigger than other, maybe it will take a very long time to come to this kind of failure. It will take many hours to come into this kind of failures, but otherwise there is not problem as such. Coming to the demagnetization of the stator or rotor. Now, in this case particularly demagnetization of stator and rotor, we find kind of orbit of the rotor and slowly it is progressing, right. So, now if out of the 7 factor, what we say that cracked rotor has a very high importance, it should be addressed immediately. Then demagnetization is the next. That means why the demagnetization happens, because what we selected is stator magnetization was a 1.4 Tesla and the rotor was a 1.04 Tesla. So, magnetization strength of the both rotor and stator must be same. However, we were not getting permanent magnet of the same strength as the rotor and the stator, because stator is a hollow and rotor was a kind of having very good thickness, while stator was we had a different configuration of the rotor and stator, that is why we were not getting this kind of same strength. However, the same strength will be welcomed, but we could not get those kind of things. However, in this case even the wear of the surfaces, even the removal of the coating to some extent was not really affecting much. So, major issue cracked rotor and the crack formation of the rotor, and then again the demagnetization. So, these things are the major issues and then we need to really think carefully. Now, coming to the back to the FMEA, we say that we need to assign the CVT ranking to the each defect. Now, what is the CVT ranking? We say no effect at all. So, the rank 1, serious effect 5. So, 1 to 5, as I mentioned, that is a relatively new product. We are going with the ranking 1 to 5, we are not sticking to 1 to 10, which was covered in the previous lecture. Another one is how frequently these kind of things are happening. Whatever the 12-15 experiment we conducted, those I am reporting, and of course, it really requires a big data set, more number of experiments are required. We found wear occurrence more frequent, more chances. Coming to the coupling failure, only we found one failure, and then even the pole formation, particularly because of the rotor cracks or the stator crack was lesser, relatively lesser. Now, rubbing on casing only in one case, particularly the when with the configuration 2 was given, and demagnetization also was more observed. Now, in this case particularly crack generation, heating and instability was also more occurred in particularly in a stator and rotor pose. Coming to the detection, how to detect this kind of failure, we find more or less not a single failure is really getting a 4 or 5, because it was relatively easy to figure out. Failure of the coupling can be seen easily, fracture of the rotor or pole formation can be easily, because we had a sheet, we could immediately use it and figure out. Now, and then coming to demagnetization, few places Gauss meter cannot be used and was slightly difficult for us, and even to finding the wear of the, because we did not have any lubricant to be analyzed. So, we were finding little difficulty compared to the liquid lubricated bearing, how to find out the wear of the particles in this situation. So, these were the ranking, and then overall RPN number, what is a risk priority number, the multiplication of these three: severity, occurrence and detection. You can see overall the failure has been shown, housing, rotor, stator and coupling, and then overall RPN number has been mentioned over here. So, if I try to rank, we say this number, the third number is crack formation has a very high ranking, 4 into 4 into 2, then comes this 24 number 2, that is again the crack formation in stator. Even though I mentioned this crack formation in stator as such was not affecting much, but basically if there is a demagnetization plus impacting, that overall really impact a lot. Coming to the third one, in this case stator pole formation has come also to 3 number, 4 number are the 2 demagnetization and demagnetization. So, now these are the 4 top 4 we need to address, or maybe we can address only 1 or 2 and then go for the next solution. So, this is what is the overall FMEA to go ahead. So, we next come to the method to reduce failure of the permanent magnetic bearing. We say magnetic strength on the magnetic brittleness increases the likelihood of the crack formation. As I mentioned, the crack formation is really playing major role. So, how do we avoid the cracks? And then one possible solution was that the way we go ahead, instead of the coarse particles, we go with the fine particle in material science. And if there are fine particles, or maybe say grain structure is made in a very fine particle, fine grain boundaries have been made in the manner that will give a better results, and it will avoid the progress of the crack. That is what has been utilized in this case. We say the merging small magnets to create a whole ring magnet. When we purchase a small magnets, so that we can get equal field for the rotor and equal field for the stator, and there is no difference in the permanent magnetic the strength. So, we are able to maintain the same magnetic strength, and then we have a more number of segments. So, cracks are already there, and there will not be chance to further crack increase in the crack. So, those things were utilized for this purpose, and then we got this work. Now, you can see here these are the square magnet which were purchased. They are very cheap, and then these magnets were embedded in into the rubber housing, and then those housings were kept in a permanent overall setup. Now, when we did it, so what we say that to prevent rotor and stator from colliding each other, rubber is used to isolate magnets and absorb the vibration. Now, if the rotor moves near the stator, and because there is a rubber available on the back side, so it can really isolate or can move little bit back side, and the way the foil bearing works. So, this whole concept was worked for was taken from a foil bearing point of view. They have a little lesser stiffness of the rubber, so it will go back easily, and the permanent magnet can have a slightly room for displacement. So, this was done. However, after getting this setup, again the experiments were conducted. So, we say experiments on the proposed PMB structure were carried out. Now, what is the problem here? Now, rotor and stator were not colliding with each other that much. What happened? The next problem came because of the rubber material. The shear strength of the rubber material is very bad, and then this had the piercing effect. That means a permanent magnet, they start piercing into this shape itself. So, cracks were developed in a rubber material, and then because once the rubber is getting cracked, then it will not have that kind of a flexibility. So, again the major problems will come. So, for this purpose then we see, instead of going for alone rubber, then we should have a aluminum housing with a rubber material and permanent magnet, and the new structure was made, and then finally a patent was filed on this, and we got a good results. So, now you can see to generate the same magnetic field on a stator and permanent magnet, so the demagnetization should not happen, and another one, they had a sufficient room to absorb the vibration or the shock from outside surface. So, there is some sort of a coasting up and coasting down behavior that can be sustained. As I mentioned, in a steady state performance, permanent magnet bearings are working well. So, if you want to operate this for the 24/7, permanent bearing will be a good solution. But if there is a frequent change, maybe they start from 0 to 1500 RPM, 0 to 3000 RPM, that coasting up period makes a lot of difference, or maybe induces a vibration, and then possibility of the collision between the rotor and stator. However, if there is some sort of a shock absorber isolators, then that behavior can be reduced significantly. So, we are trying to bring some sort of damping from outside environment, and then there was a change because we were not getting the same strength magnets. If we get same strength magnet stator and rotor, then we don't have to go with the square magnets, then we can directly use it. But if we don't get it, then how do we really come up with a solution? That has been shown in this overall. Finally, the results were, as I mentioned, the patent was filed based on this. That now coming to the summary. And of course, in this I covered this case study, reason being that new products can be developed when we have a failure mode and effect analysis, and more creative ideas will come. As many times we assume there is a one problem, but we try to solve that problem, that may give you the two problems. When again you try to solve those two problems, then four problems may emerge. But sequentially, if we try to address all those, we will get a good solution, and that is what the beauty of the failure mode and effect analysis. So, what is the summary of this lecture? We say failure mode and effect analysis on a permanent magnetic bearing was maybe the device and maybe used on this one. We figure out around 13 possible failures of the passive magnetic bearing. We calculate the RPN for each failure, and then whatever the most important failure was basically the decrease in the magnetic field, and then I given a reason that if there is a difference between the magnetic field of the rotor and stator. If you can bridge this gap, then some solution will come. That is why we use a square magnet in rubber material and aluminum material. So, this is one. Then another was a non-uniformity of the magnetic field. This was another, when we are using small the square magnet, we could reduce a non-uniformity. Now, whatever the non-uniformity is already known to us, is not going to change significantly. So, we can modulate and we can optimize it. Another, we found a new formation of the poles, there is a rubbing, and now because of the new configuration, there is no worry about the new formation of the poles. And last one is a fracture of magnet. We use a square magnet, so that already it has been fractured and no further expansion of the crack will be possible, and there is sufficient damping for the coasting and a coasting down. So, whatever the major issues, we will try to solve it. Now, in this case, the last one is a rubber isolator in aluminum framework could be used to prevent the magnets from combining or becoming the damaged. So, these were the these are two sequential case studies. The methods were used, FEM mode and the failure mode and effect analysis were used for this purpose to give a good solution to us. Hope this will be useful to you, and then you can implement on some of your projects, and then get a good result. Thank you for your attention, and we will cover the maintenance aspect in next lecture. Thank you.